Hi viewers, welcome to my class on mechanics of materials. In today's class, we'll work out another numerical example on shear force and bending moment diagram with a coupled and UDL acting on the beam. Let us start. For the beam shown in figure, determine the load P acting at C such that the reactions at supports A and B are equal. Draw the shear force and bending moment diagram indicating the values at the salient points. Locate the point of contraflexure. This beam is supported at A and B and is subjected to a UDL of intensity 48 kN per meter and coupled 30 kN meter. At point C there is a load, the magnitude of which is unknown. Now we have to find out the load P such that it produces equal reactions at the supports A and B. So RA and RB are the reactions, but it's given that RA is equal to RB. So for such equal reactions you have to find out the load P and then you have to draw the shear force and bending moment diagram and locate the point of contraflexure. This beam has to be in equilibrium under the action of these applied loads and reactions. So you can take moment summation with respect to any point on the beam and equate that moment summation to 0. So here there are three unknowns, but since it is given RA is equal to RB, this reduces to two unknowns. RA is equal to RB, so it's only one unknown and unknown load. So there are only two unknowns now. So to eliminate one of the unknowns, you need to take moment summation with respect to C. So which eliminates P and you will get only one unknown. If you take with respect to point A, RB is unknown, P is unknown. So we will get two unknowns into the equation. The same if you take with respect to point B also. If you take with respect to point C, RA and RB will come into the equation, but RA is equal to RB, that is only one unknown. So the best way to find out the reactions is by taking the moments under respect to point C. So let us take the moment summation with respect to point C. So summing up the moments, you get sigma MC RA into, it's producing a clockwise moment, and the distance with respect to C. So this producing a clockwise rotation with respect to C. RA into 4 plus 2 plus 1, 7. RA into 7, which is producing a clockwise rotation with respect to C. Now this UDL 48 kN per meter, it's acting over a span of 4 meter. So the resultant load is 48 into 4. 48 into 4, but this will produce a counterclockwise rotation with respect to point C. And the location of the load is center of 4 meter, that is 2 meter from here. Okay, so resultant load will act 2 meter from D, or from the support C it is 3 plus another 2, 5. So 5 meter. 48 into 4, the resultant load into 5, that will produce a negative moment. This couple will produce a clockwise moment, it's 30 kN meter. So irrespective of the location of moment center, this couple is acting clockwise. So you have to add plus 30. So plus 30, and now the RB is producing clockwise moment, and the moment produced by that is RB into distance is 1, RB into 1, that summation is equal to 0. We know RA is equal to RB, we can substitute as R. So you get 7R, instead of RA I am substituting as R. 7R minus 960 plus 30, and again RB is R, so that is equal to 0. Now 8R is equal to 930, or R is equal to 116.25. So you get that reaction are 116.25. At A and B you have equal reactions of 116.25. After getting the reactions, you can find out P by summing up the forces and equating to 0. If you sum up the forces, you get RA minus this UDL. This will not come into the force summation because due to a couple, the net summation of force is 0, plus RB minus P is equal to 0. So this is RA plus RB is 2R minus this UDL, that is 48 into 4, minus P is equal to 0. R is known, so from that P you get as 40.5 kilonewton. So we solved the unknown reactions and the load acting at C. After getting the unknown reactions and load, we can draw the shear force and bending moment diagram. So let us calculate the shear force at various points. Since here UDL is acting, you have to take a section immediately right of A and immediately left of D. And due to couple, shear force will not make any change locally. At that point, shear force will not change. But due to this couple, the reactions will change, and that will produce an overall effect on the shear force diagram. But as such, at that point, shear force will not be affected. So for getting the reactions, you have to take this moment, and in the moment summation always you should take. But in force summation or shear force summation, as if this couple is not existing, you have to draw the shear force diagram. Only bending moment you have to consider this. Otherwise, for drawing shear force diagram, you need not consider this couple. So you have to take section immediately right of A and immediately left of D. Immediately right of A, you have 116.25. So when you take a section and look at this left side, you have only one force, 116.25. So right of A, it is 116.25. Now when you go to left of D, you have two forces on left side here, this portion. So left of D is the section and you are looking for these forces. You have 116.25 minus complete UDL will come there. So 48 into 4. So 116.25 minus 48 into 4, you get minus 75.75. That is the shear force left of D, immediately left of D. Now this section you can take, couple we need not consider. At this section you can take dB. Here shear force will be constant. So here at this section there is no further load added, so you will get the same shear force. Even at D you get the same, even at dB you should get the same. So at this section dB, this 116.25 minus 48 into 4 only. No further load is there. So that will be the shear force in the section dB. Same as this, minus 75.75. In the section BC, there is one load added, and here you got minus 75.75, and this section you should add this reaction. Since it's upward, it will increase the shear force by this amount. So minus 75.75 plus 116.25, that will give the shear force in the section BC. So in the section BC, 116.25, I just shown the summation from here, 116.25 minus 48 into 4 plus 116.25, that is equal to 40.5. This is already there here, so plus 116.25, 40.5. So you got the shear force on various sections. Now let us calculate the bending moment at various points. Bending moment at A is 0. Since no moment is acting, so it has to be 0. When a couple acts at any point, you have to calculate the bending moment immediately left of that point and immediately right of that point. So here at D the couple is acting, and immediately left of D without including the couple you have to take the moment summation. Immediately right of that point the same moment summation for these forces you will get. So you are only moving an infinitesimally small distance immediately right of that point. So when you take the right of that point, you have to include the couple. Okay. So left and right of that point, left without including this couple and right taking this couple. You can calculate the bending moment like that. So you have to calculate immediately left of D. Left of D without couple. 116.25 is producing a clockwise moment. 116.25 into 4. Okay. Now this will produce a counterclockwise moment with respect to this section. So 48 into 4 is a load. We are only just infinitesimally small distance left of D. So 48 into 4, the total UDL is there. 48 into 4 and it will have 2 meter away. So 48 into 4 into 2 and it is producing anti-clockwise moment. So the resultant is 81 kilonewton meter. That is immediately left of D. Immediately right of D, you have to include the couple. So the moment produced by all these forces will remain same because you are only moving just small distance away. So the moment of these forces will remain same. You should add this couple 30. So bending moment right of D is the same summation is there. This summation is there plus 30. So that will give 111 kilonewton meter. That is the bending moment right of D. So what is the effect at that point D where couple is acting? Couple will increase the bending moment by that amount 30. So at D, left to right of D, there is an increase from 81 to 111. And because of the clockwise couple, the bending moment will increase. If it is an anti-clockwise couple, it will decrease. So if it's an anti-clockwise couple of the same magnitude is acting, then you should subtract. Instead of plus, you should take minus. You will get a decrease at that point. So wherever a couple is acting, and on the bending moment diagram, there will be a sudden increase at that point. So left to D, right of that point change means the change has to happen at point D. So bending moment is changing suddenly at point D. By 30 it is increasing. Okay, next you have to take the bending moment at B. Bending moment at B, you have to consider all these two loads and this couple. So when this will produce a clockwise moment. Distance is 6 and this will produce an anti-clockwise moment. 48 into 4 is a load. 2 plus 2, 4 is distance. So 48 into 4 into 4 anti-clockwise moment. This you can add plus 30. So 116.25 into distance is 6 clockwise moment. 48 into 4 into the distance is 2 plus 2, 4 plus couple is 30. So that will give the bending moment as minus 40.5 kilonewton meter. And bending moment at C has to be 0. And no couple is acting there, so bending moment at C has to be 0. So that completes the bending moment calculation. You may have to calculate the bending moment under UDL also, where shear force is changing its sign, and we got a change of sign in the shear force. So we need to calculate the bending moment corresponding to that point also. Let us first draw the shear force diagram and observe the change of sign. Now we got the shear force immediately right of A and immediately left of D. Right of A you had 116.25 and left of B minus 75.75. So the change in the section AD is 116.25 to minus 75.75, and that variation will be linear variation. So you can show that by linear variation, 116.25 to minus 75.75. That is in the section AD. Right of A to left of D you should show linear variation. And here it is constant. No load is acting between D and B, so shear force is constant. And we got in the section DB as minus 75.75. And in the section BC also it is constant. We got the value as 40.5. And here it will change. That is in the section DB to section BC. The change will be due to this point load. Point load is 116.25, so it will increase by that amount. You have to show the two horizontal lines. Here you know is minus 75.75, here it is 40.5. So that completes the shear force diagram. But we are getting a change of sign for shear force. Shear force is changing its sign here. Okay, so from positive to negative shear force. So shear force is coming to 0 at this point. Corresponding to this, you will have a peak point for the bending moment curve. So that peak point you should mark in the bending moment diagram, and also you should calculate the corresponding bending moment. So to locate this point, you can use a similar triangle method, but I am going for the shear force equation. You can use similar triangle method which I explained in one of the earlier classes. Here I am going for writing the equation. Let us consider a section at a distance x meter in the portion AD where shear force is coming to 0. Now when we consider the forces left side of that section, you have two forces, 116.25 and this portion of the UDL. This portion of the UDL is 48 kilonewton per meter. For x meter it is 48x. 48 kilonewton per meter. For x meter it is 48x kilonewton. So 48x will be the load, downward load. So 116.25 minus 48x will give the shear force. 116.25 minus 48x is the shear force for the section AD. So you can use for x values from 0 to 4 meter. This equation is valid, and you can find out the shear force by substituting any value between 0 and 4. But we are locating this point where shear force is known. So shear force is known and we know that it is coming to 0. And that's why I am equating this to 0 and I am solving for x. I am not finding out shear force. I already know the shear force at this location. I am finding out at what distance this shear force is coming to 0. So by solving this, you get 2.422 as the distance x. So at a distance of 2.422 meter, the shear force is coming to 0. So corresponding to this distance, you have to calculate the bending moment and mark it on the diagram. So you can write down the bending moment equation. Bending moment equation, the same forces are there. You are calculating bending moment for this point, and that point is in the section AD, and we have already taken that section. Now you have to write down the bending moment equation for that section. You can see two forces. The same two forces are there. So this will produce a clockwise rotation, and the moment of that force is, we just multiply with the x, and this force is downward force, negative moment. Already force is known, 48x, into the distance is going to be x by 2. Already force is written here. You need to multiply with the corresponding distance where that force acts from the section. So 116.25 into x, okay, minus 48x, it is producing negative shear force and negative bending moment. So minus 48x will remain same. You have to only multiply with the distance, x by 2. So you multiply this with x and this with x by 2, that will give the bending moment. So bending moment is 116.25x 116.25 into x minus 48x, the load, into the distance x by 2. That will give the bending moment equation. Now substitute x as 2.422. So that will give the bending moment corresponding to this point, and that is going to be the peak point for the bending moment curve in this portion. Now let us plot the bending moment curve. Shear force diagram I already explained. Now bending moment you should plot. In the section AD, the bending moment variation is parabolic with a peak coming corresponding to this point. So that is at a distance of 2.422 meter and the peak is coming. So you should show parabolic variation. We got value 0 and 81 kilonewton meter. At 0 here at A, at left of D it is 81 kilonewton meter. Left of D means it's almost D only, immediately left of D, so up to D. So 0 to 81 kilonewton meter with a peak coming here. If there is no peak, you can even draw it like this. A parabolic curve you can draw like this. If you are not getting any peak, without peak you should draw the parabolic curve like this, continuously increasing. Since shear force is changing its sign, you should draw a peak. It should increase to that value and then decrease to 81. So this way you should plot the bending moment curve for that portion. And here you are having the peak, and the peak value is 140.77 kilonewton meter, which you have already calculated. So you can draw the bending moment diagram for this portion. And at this point we know, since the couple is acting and the bending moment is suddenly increasing by 30. So immediately left of D to right of D you have that change. Immediately right of D you have calculated the bending moment 111, and at B it is minus 40.5, and the variation is going to be linear because shear force is constant or no load is acting, so bending moment is going to vary linearly. So right of D to B you can join, and left of D you have 81, so 81 to 111 is in at D, because left to right there is a change, so that is a change due to that couple acting at that point. So the bending moment has to increase by 30. Due to clockwise couple, it will increase by that amount. If it's an anti-clockwise couple, it will decrease. From that value, it will decrease suddenly. Now from minus 40.5 at the extreme right end, it is 0. So you have to show linear variation once again, since shear force is constant or no load is acting on this part of the beam. Now there is a point of contraflexure. Now we need to calculate that point of contraflexure. Point of contraflexure is this point where bending moment changes its sign. And to locate this point of contraflexure, this point is coming in the section DB, and we can write down the bending moment equation for this section and equal to 0. If you can take this section at a distance x, so this will produce a clockwise moment, and this load will produce an anti-clockwise moment, and couple is there, clockwise couple is there. So these three moments you should take and sum up and equal to 0. That will give the distance x. So let us do that. Now I have taken a section at a distance x, and this section is in the portion dp, because we have identified the point of contraflexure in the section dp. So the moment produced by this is 116.25 into x, clockwise moment, and this load is 48 into 4. The load is 48 into 4. That will act at the center of this UDA. When you consider this section, the total load is the total load is 48 into 4. It acts at a distance of 2 meters from here. So from the section considered, it will be overall x minus 2 meters. So it will be x minus 2. So this distance is going to be x minus 2. X minus 2. The location of the resultant load is 2 meters from here. So from the section it will be x minus 2. So minus 48 into 4, that is a load, into x minus 2, that will give the moment produced by this, plus 30, this clockwise couple, you should add plus 30, that will be the bending moment at this section. Now that you have to equate to 0. So 116.25 x clockwise moment, 48 into 4, that is the load, that will is at a distance x minus 2 plus clockwise couple 30, that can be equated to 0. So you will get this equation, and it's a linear equation because it's a straight line variation. You can also try similar triangle method to get this point, but if a variation is parabolic, you have to write down the equation. So you need to practice to write down the equation. So by solving this, you will get x as 5.465 meter. So that is 5.465 meter is the distance from the left hand. That is this distance from here to this point is 5.465 meter. So this is a point of counterflexure. So we have drawn the shear force diagram, bending moment diagram, located the maximum bending moment, and this is the maximum bending moment over the beam 140.77, and also we have located the point of counterflexure. That's all for today. Thank you for watching.